Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at metallic bonding. We're going to talk about what metallic bonding actually is, how metallic bonding arises, factors that affect the strength of metallic bonding, and link some properties of metals to metallic bonding. Before we talk in detail about metallic bonding, there are a few essential ideas you need to be comfortable with. Atoms are made up of protons, neutrons, and electrons. Negatively charged electrons exist in orbitals around a positively charged nucleus. Each orbital around an atom can hold one pair of electrons. Opposite charges attract. A charged particle is high energy and unstable. The closer it gets to an opposite charge, the more stable it becomes. As a result, opposite charges attract and will always try to get as close to each other as possible. The closer they are, the stronger the force of electrostatic attraction, and the harder it is to pull them apart. Because of this, the further electrons are from the nucleus of an atom, the higher their energy and the more unstable they become. It is the electrons furthest from the nucleus in an atom that get involved in reactions and bonding between two atoms. These electrons are called the outermost electrons and make up the surface of an atom. Recap done? Let's go! To become more stable, metal atoms lose electrons to get a lower energy electronic configuration. Usually, in a chemical reaction, the metal atoms can lose their electrons by giving them to something else, often a nonmetal atom. When they do this, they become positively charged ions. But what if there are no other atoms other than the same type of metal atom around? The metal atoms will still want to lose electrons to have a more stable electronic configuration, and yet there is nothing available to take the electrons. The outer shell electrons are held weakly by the metal atom's nucleus. And this means they will kind of drift further away from the nucleus, temporarily leaving the atomic orbitals of the atom. The atom cannot actually lose the electrons as nothing is available to take them, and yet the electrons no longer really belong to the atom. The electrons are said to be delocalized. As electrons have effectively drifted out of the atom's atomic orbitals, a positively charged metal ion is left behind. The delocalized electrons from the metal atom will still be attracted to the positively charged metal ion and remain close by. This can seem strange at first. Electrons leave an atom's electron orbitals, and yet the electrons stay close to the ion formed. Let's have a look at sodium as an example. Sodium has one electron in its outer shell and wants to lose an electron to get that stable configuration of 1s2, 2s2, 2p6, forming a positively charged sodium ion in the process. There is nothing else available to take the electron no longer held by the sodium. As the electron is negatively charged, it gets attracted to the positively charged sodium ion and hangs out close to it, constantly moving, creating an area of electron density around the ion. The electron doesn't rejoin the ion to form an atom. It is far enough away to remain separate from the ion and is called a delocalized electron as it isn't held in one place or orbital. This isn't really a very stable arrangement and wouldn't ever happen by itself to just one atom. However, in a solid piece of sodium, there are billions of sodium atoms all trying to do the same thing. Now, each positive sodium ion is attracted to the electron densities of delocalized electrons around other sodium ions. This pulls in all the sodium ions close to each other. The delocalized electrons are now attracted to many positive charged ions of sodium and are free to move around all of them, creating what is called a sea of delocalized electrons. This sea is a bit like a flowing negatively charged glue that the positively charged ions are attracted to. This arrangement of ions and delocalized electrons is called metallic bonding and explains how atoms are held together in metals. The structures formed by metallic bonding are repeating lattices that have an infinite possible size. As metallic bonding is basically just a force of attraction between positively charged metal ions and delocalized electrons, the strength of the bonding in a metal is based on this attraction. The strength of attraction between oppositely charged particles is determined by two things: the distance between the particles and the size of their charges. These are sometimes linked together by charge density. The higher the charge density, the smaller the ion and the greater the charge. Small metal ions with a high charge will have a stronger attraction to the sea of delocalized electrons in the lattice compared to larger metal ions with a smaller charge. Smaller ions have a smaller ionic radius, meaning the distance between the positively charged nucleus of the ion and the delocalized electrons is smaller, given a greater force of attraction. This means it is harder to separate the ions given stronger metallic bonding. Larger ions have a larger ionic radius, meaning the distance between the positively charged nucleus of the ion and the delocalized electrons is greater, leading to less attraction given weaker metallic bonding. Higher charges also mean greater attraction. For example, take sodium and aluminium. Atoms of sodium form ions with a 1+ charge, and atoms of aluminium form ions with a 3+ charge. Sodium ions have a larger ionic radius than aluminium ions. In the aluminium structure, there will be 3 times as many delocalized electrons as in the sodium structure, as each aluminium atom has lost 3 electrons compared to each sodium atom losing only 1. The aluminium ion has a 3+ charge, and the smaller ionic radius means much greater attraction between the ions and delocalized electrons. This pulls the ions in tight and gives solid aluminium a high density and melting point of 660 degrees Celsius. Sodium, however, with only 1+ ion charge, that larger ionic radius and fewer delocalized electrons, has a much lower melting point of 98 degrees Celsius. Clearly, it takes less energy to break apart the solid sodium structure, and this means the metallic bonding in sodium must be weaker than in aluminium. The delocalized electrons from metallic bonding also give metals unique physical properties, most notably the ability to conduct electricity and thermal energy, heat. Electricity is essentially the flow of charge. As electrons are negatively charged particles, a net movement of electrons through a substance means the substance has electricity flowing through it. It is conducting electricity. Metals are able to conduct electricity as the delocalized electrons in their structures are just that, delocalized. They are free to move and can be forced to flow from one end of the metal to the other. Thermal energy is transferred through a solid by the vibration of particles within the solid. As each particle vibrates, it causes a neighboring particle to vibrate, and so on. Eventually, all the particles will be vibrating equally, and the energy has spread from the area heated to the whole solid. When metals are heated, the high density of ions means particles can easily vibrate other particles and spread the energy. But the real trick is that the delocalized electrons are also free to move, meaning they can further help transfer the energy through the solid. So, to summarize, metal atoms, or more specifically ions of the metal atoms, are held together in a solid by metallic bonding. Electrostatic forces of attraction between positively charged metal ions and a sea of delocalized electrons. Metal atoms lose electrons to get a more stable electronic configuration and form positively charged ions as a result. If only metal atoms are present, there is nowhere for the lost electrons to go, and they remain attracted to the positively charged ions, although they don't rejoin the ion's atomic orbitals. The electrons are delocalized. Positively charged ions get attracted to delocalized electrons from other metal atoms, and this pulls the positively charged ions close together, forming a dense solid, except for mercury, at room temperature. The strength of metallic bonding within a metal is based on the size and charge of ions. Metals with small ions with a high charge will have stronger metallic bonding in their structures than metals with large ions and a lower charge. Delocalized electrons are free to move in metals, meaning they are good conductors of electricity and thermal energy. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.